Hi everyone, welcome to another EMWorks webinar. Today's topic is going to be inductor design in using EMS. Our agenda for today begins by talking about ferrite cores, their properties and what are they good for. Then we're gonna look into the design specifications we have for today's design. And from there, we're going to go into details of design. We're going to begin by selecting a core, and then we're going to show you how you can actually design an inductor in EMS and check if inductor performances match the specifications. We're going to wrap up this webinar by a short discussion. So ferrite materials have been invented in 1930s at Tokyo Institute of Technology. They're basically a ceramic compound material of iron oxide with some metallic elements. They have very low core loss, which makes them very attractive for high frequency filters and inductor designs. Another good thing about them is that they can be gapped. Basically, an air gap can be machined into the core, which is a useful thing in two different ways. One thing is that it effectively reduces the slope of the BH curve and prevents your core from saturating, which is very important for ferrites because they have very low saturation point, sometimes as low as 0.2, 0.253 Teslas. Another good thing about having an air gap in the core is that core helps define the inductance value. If core does not contain an air gap, then the inductance value can fluctuate almost. It's difficult to keep it within tight boundaries because the manufacturing process can introduce many different variations which are difficult to control if there is no air gap. However, if there is an air gap, then it is the value of inductance is much more easy to keep at certain value. So design specifications we have for today look like this. We want to design a continuous mode inductor, meaning that the current through inductor doesn't go to zero. It has a significant DC bias, and the ripple does not bring it below zero. The current we have is 1 amp with 10% ripple, which defines the maximum current value we want to work with, and in turn defines the wire gauge. Another thing we can conclude from these specifications being continuous conduction mode and only 10% ripple is that the core loss is not going to be very important. The AC component of the current is not very significant, meaning that most of our losses are going to be in the copper. The inductance value we are targeting is 0.25 millihenries. The maximum B field, we don't want to saturate our core, so the maximum B field should not exceed 0.3 Tesla, meaning the flux density in the core for 1.1 amp of the current should not be higher than 0.3 Tesla. We also have, as a specification, we have maximum allowable power loss to be 0.3 watts, which in turn defines the maximum resistance value we can have in the coil. We're going to work with a coil factor of 0.6, which tells us how much of the space for the coil we're actually using for copper and how much ends up being air gaps between wires or insulator between wires. So from these specifications, let's move to the first step in the inductor design, which is a core selection. You see, when designing an inductor, there are many different variables to play with. All the core geometries, or all the core geometrical dimensions, or all the coil parameters such as number of turns, wire cross-section area, the air gap length. So all these variables have to be set before you can have your final design. So it's sometimes difficult to start, but you gotta start somewhere, and usually it is good to start by selecting a specific core shape. Today we're going to be working with an E-shaped core. They're very widely available. They come in many different shapes and sizes, and they are very easy to wind. When selecting a core size, it is very useful to rely on a coefficient called core geometrical constant. This single number ties together three different, very important geometrical features of your core, which are the cross-section area of the yoke, AC, then window area which tells you how much space you have for the coil, and the mean length of a turn, which tells you how long the average turn is going to be. So when you bring in these three variables into one formula, you get this kg, which is core geometrical constant. So you can use this number here to select the minimum size of your core, which is going to satisfy the predefined specifications. The way it's done, you bring in all these specifications we talked about, like inductance, maximum current, flux density, resistance, and fill factor. You bring them into this one formula, which gives you a number, which in our case is 0.9 10 to the minus 3 centimeters to the 5. This number defines the minimum kg value we can accept. So for this design, this value turns out to be 0.9 10 to the minus 3, which says, if you look at the core data sheet with geometrical constant pre-calculated, that the minimum core size we can work with is EE16. So now that we have a core selected, we can move to selecting other features like the number of turns, air gap length. For the selected core shape and wire cross-section area and the fill factor, it turns out that the maximum number of turns we can put in this core is 60. So if you decide to do your first iteration of your design with 60 turns in the coil, then you can move to selecting an air gap, and for this first iteration you can then check if the losses and the flux density are within the set boundaries. To do this, we'll move to the EMS and look at first look at the core shape we have selected. This core has an air gap, so let me just hide the coil so that you can see the air gap in the core. This air gap is defined by this cut feature right here, and if we want to make this air gap length parameter for the EMS study, we should select this the length of this cut feature and add this dimension to the EMS. So like this, we have made this dimension available to the EMS, so EMS can work with it and make it parameter to its study. So let's go to EMS and select new study. We're going to do a magnetostatic study with parameterization. The first thing when defining any study in EMS is defining materials. So for air, we're going to apply air. Let me make the coil visible again. So for the coil, we're going to use copper, and for core, we're going to use a material which from the EMS library called typical ferrite. Like this. So now let's go and define the coil. We're going to use a wound coil. Select the part, and now we got to select the entry port of the current in the coil. To make it easier, let's first hide the core, and then select this face right here. So now you can see which way the current is going to circulate through the coil. As we've said, let's use the maximum number of turns we can put in through this core. And the current per turn is, we said, 1 amp with a 10% ripple, which makes maximum current of 1.1 amp. Here we can mesh the geometry. Once mesh is done, this study will be ready for analysis. One more thing, I forgot to do parameterization. So let's go to design scenarios, and here, as you can see, this dimension is already available to be parameterized. Here you can select the step size for which you want to change the length of the air gap, and the starting and the initial and the final value. So now let's go and look at the results in a pre-run study. Let me show the core, and we don't need air. So first, let's look at, in the results table, at inductance values for different scenarios, which mean different air gap lengths. If you remember, we were targeting 0.25, if I remember correctly, millihenries. And we can see that this value is fulfilled for scenario number 12, which is, if I'm not wrong, 0.775 millimeters. So you can see how inductance changes for different air gap lengths, and as expected, it drops down for higher air gaps. However, this value of air gap from scenario 12 pretty much accurately matches the inductance we were looking for. Now we gotta make sure that the resistance does not exceed those 250 milliohms from our design specifications, and indeed it doesn't. It is only 4.4, actually 45 milliohms, which is well within the boundaries. Finally, let's go and check the flux density in the core. You can the way this plot here is made is by selecting 3D fringe plot with section clipping. Then here you can select the plane you want to use to create your plot, and of course we gotta select the right scenario. our design, the inductance value we're looking for is achieved for scenario number 12, so this is the scenario we're going to use. And as you can see, the inductance value stays within this 2.8, 2.9 zone in the yoke, which keeps this core out of saturation. So this is how we have quickly reached the optimal design of a continuous current mode inductor in EMS. In case you wanted to perform a simulation or a design of a coil which has high AC component, an AC component with high magnitude, and you wanted to make sure that the core losses are still within certain boundaries, meaning that they are more significant in this case, and then that you wanted to get a closer look at the core losses in your core, you would have to do an AC magnetic study. First, define the frequency of your AC current component, for example, 5,000 Hertz. You would uncheck the split core loss. You want to get the total core loss in your core. You would check these compute circuit parameters if you want to get the circuit impedance, induced voltages, and stuff like that. Again, you would have to define material for your parts. For core, you could select from different nonlinear materials we have in the EMS material library. For example, M27. And then if you select this material and then go and edit it, you can define the BH curve of the material. You can define, which is the most important in this case, the core loss method for computation of core loss. And in this case, we're going to select power ferrite. And here you can select the coefficients of your specific ferrite material. Common values are 1 for alpha, 2 for beta, and 4 up to 8 for K. Again, you would define the same coil. However, this time it might have higher current magnitude. Again, we will have to select the entry port, define number of turns, and maybe have higher current RMS value. So this is how you would. I'm not going to run this simulation right now, but this is how you would compute core losses in EMS if your design featured something like high. If your design featured strongly pronounced AC component of current. So now let me summarize what we did in EMS. We showed how you can use EMS to design an inductor for both continuous and discontinuous current conduction case. We showed you how you can easily use the full, how you can take advantage of the fact that EMS is part of SolidWorks, and you can take advantage of this to easily parameterize different dimensions and see how your results change for each case. You've seen how easy it is to get copper and core loss calculation in EMS, and at the same time get inductance and resistance values computed for you. So I would like to thank you for your attention and invite you to check some more applications of EMS on our website, check some other YouTube videos. You can contact us on this email address or on this phone number. And now, if there are any questions, I would like you to type those questions in the chat box, and I would be happy to answer them for you. So if there is no question, I would like to thank you for your attention. And okay, there is one question: what ripple frequency was assumed? For the first case, thank you for your question. For the first case, we have assumed that the AC ripple is not very significant, and we have designed a magnetostatic study, which does not take into account the AC ripple frequency at all. But if you wanted to do if you had a case where your AC ripple is important, then I would advise you to do an AC magnetic study the way I showed you, and then run a simulation for certain frequency. AC magnetic study is basically a frequency domain analysis. So you would you would type in the frequency of the ripple you're interested in, and then run an AC magnetic study. Sure. So the other question is, how can we apply a pulse current waveform or any other shape of waveform in EMS? To do this, you would have to rely on something which is called transient magnetic study. It's a time domain analysis, and here let me briefly show you how you can define coil. When you're defining a new coil, you can select many different shapes for your current. There is a pulse, there is sine, there is exponential, DC. However, you can also import any random current, any current wave shape you're interested in, and you will be able to simulate that in EMS transient analysis. So for cases like that, for random or for basically any current waveform you're interested in simulating other than sine or DC, then you will have to use transient analysis. No problem. Okay, guys, if there is no more question, I would like to thank you for your attention, and I'm looking forward to doing another webinar with you soon. Thank you.